Tonight we're going to talk about a message that was sent to the stars nearly 50 years ago, and why no one who sent it will ever hear a reply. On the 16th of November 1974, on a warm afternoon in the hills of northern Puerto Rico, a crowd gathered under a white tent beside the largest radio telescope humanity had ever built. The dish itself was more than 300 meters across, pressed into a natural limestone sinkhole and lined with nearly 40,000 aluminium panels, each one angled to catch the sky. It had been standing there for more than a decade, listening to pulsars and mapping distant galaxies, but on that particular afternoon it was about to do something it had never done before. It was going to speak. The occasion was a ceremony marking the completion of a major upgrade to the telescope's transmitter, and the engineers and scientists gathered there had decided to mark the moment with something symbolic, something that would demonstrate the newly installed power of the instrument in a way that felt appropriate to its scale. What they chose to send was a picture, encoded in ones and zeros, a message just over 1,600 bits long that described, in the simplest terms they could devise, who we were and where we lived. It included a diagram of the solar system, a sketch of a human figure, the structure of DNA, and a few other details that seemed, at the time, like the essential facts of our existence. The message was aimed toward a dense cluster of stars called Messier 13 in the constellation Hercules, and it was transmitted at a frequency of 2,380 megahertz on a beam so tightly focused that if you had been standing anywhere else in the universe, you would not have heard it at all. The transmission itself lasted less than 3 minutes. During those minutes, the binary data was converted into a warbling audio tone and played over loudspeakers for the audience, a rising and falling hum that sounded to some who were there like the voice of a machine trying to sing. People left the tent and stood in the grass, looking up at the great dish as it hummed and clicked and sent its patient string of numbers out into the dark. And then it was done. The message was gone, climbing away from the earth at the speed of light, and the people who had built it and sent it went home. What almost none of them said aloud, and what the ceremony itself did not dwell on, was that the cluster they had chosen as their target was roughly 25,000 light-years away. The signal would not arrive for 25,000 years. If someone there received it, understood it, and immediately sent a reply, that reply would take another 25,000 years to return. The entire round trip, question and answer, would require 50,000 years, a span of time longer than all of recorded human history, longer than the entire span of human civilization as we understand it, longer than our species has existed in anything resembling its current form. The message sent from Arecibo that afternoon was not a conversation. It could not be. It was a gesture, a demonstration, a kind of technical poetry, but it was not an attempt to speak with anyone. It was, in the most literal sense, a message that could not be answered, not by the people who sent it, not by their children, not by any generation that could trace a continuous line of memory back to the afternoon it was transmitted. And yet it was celebrated as a message, framed as an act of communication, written about in newspapers and magazines as though something had been said and someone somewhere might one day say something back. This is where we begin. Not with the silence of the universe, which has been written about endlessly, and not with the question of whether anyone is out there, which is a question we may never answer. We begin instead with a different kind of silence, one that has nothing to do with whether civilizations exist and everything to do with the geometry of the universe itself, because the problem is not that we have not heard from anyone. The problem is that even if they are speaking, even if they have been speaking for thousands of years, and even if we one day hear them clearly, we cannot speak back in any way that resembles a conversation. The speed of light is absolute, and the distances between stars are vast, and the consequence of those two facts together is that any two civilizations separated by more than a few dozen light-years are condemned to something that looks, from the outside, like dialogue, but feels from the inside like shouting into a well and waiting for an echo that will not come, until everyone who shouted is long dead. Distance does not merely delay contact. Beyond a certain scale, it turns conversation into archaeology. And the universe, it turns out, enforces that scale on nearly everyone in it. By the end of tonight, you're going to understand exactly why the Arecibo message was not a conversation, why even the nearest stars are too far away for dialogue as we know it, and why the silence we hear when we listen to the sky may not be absence at all, but simply the inevitable loneliness that the universe's geometry imposes on everyone who tries to speak across it. We are going to sit with the people who first tried to listen, the people who believed that hearing would be enough, and the mathematics that slowly, quietly closed the door on the idea that we could ever be neighbours to anyone who was not already close enough to touch. And we are going to follow the long, patient arc of a message sent into the dark and ask what it means to speak when you know, with absolute certainty, that you will never hear a reply. Now, let us begin. Consider for a moment what it would mean to hold a conversation with the nearest place outside our solar system, where a conversation might, in principle, be possible. The closest star to the Sun is a small dim red dwarf called Proxima Centauri, and it sits, by the standards of the galaxy, almost unimaginably close to us. The distance is just over 4 light years, a span so short that astronomers sometimes speak of it as though it were trivial, as though 4 light years were a kind of cosmic next door, and in a certain sense it is. There are hundreds of billions of stars in the Milky Way, most of them thousands or tens of thousands of light years away, and Proxima Centauri is so near that if you were to make a scale model of the galaxy in which the Sun was the size of a peppercorn, Proxima would be another peppercorn about 1 kilometre away. Close by the standards of the model, close by the standards of the galaxy, but not close by the standards of conversation. In 2016, astronomers using a telescope in Chile announced that they had detected a planet orbiting Proxima Centauri, a world they called Proxima Centauri b. It was roughly the size of Earth, and it orbited its star at a distance that might, under the right conditions, allow liquid water to exist on its surface. The discovery was treated as extraordinary, and in many ways it was. Here was a world, rocky and temperate, orbiting the nearest star to our own, a place that was, by the measure of interstellar distances, as close as a world could possibly be without being in our own solar system. And yet the discovery also clarified, in the starkest possible terms, just how far away even the closest stars really are. If we sent a message to Proxima Centauri b today, travelling at the speed of light, it would arrive in 4.25 years. If someone there received it, understood it, and immediately transmitted a reply, that reply would take another 4.25 years to return. The total round trip, from the moment we asked a question to the moment we received an answer, would be 8.5 years. Not 8.5 minutes or 8.5 hours, but 8.5 years. A child born on the day we transmitted the message would be in 3rd grade by the time the answer came back. A college student would have graduated, found work, possibly started a family. A marriage that began on the day of transmission might, by the time of the reply, have ended. And Proxima Centauri is the nearest star. At 10 light years, the round trip takes 20 years. At 20 light years, 40 years. At 50 light years, the distance of several dozen sun-like stars within what astronomers sometimes optimistically call our local neighbourhood, a single exchange of question and answer takes a full century. The person who asked the question would almost certainly be dead by the time the answer arrived. Their children might be old, their grandchildren would be middle-aged. This is not conversation. Conversation is a living thing, a rhythm, a dance of statement and response that happens quickly enough to feel continuous. It is what allows us to build shared understanding, to negotiate meaning, to feel that we are not alone. The rhythm of conversation is measured in seconds, occasionally in minutes, almost never in hours. A delay of even a few seconds begins to feel awkward, a few minutes strange, a few hours something else entirely. What conversation requires, more than anything else, is immediacy. The sense that the person you're speaking to is present, reachable, able to respond before the context that gave rise to your words has shifted or dissolved. Interstellar messaging has none of that. It is not a dialogue. It is a broadcast, a transmission sent into the dark with no assurance that it will ever be received, and if it is received, no expectation that the sender will live to see the acknowledgement. It is closer to leaving a note on a table before going away forever than it is to speaking with someone across a room, and yet we call it communication because we do not have another word for what it is. We call it sending a message, because the alternative, saying that we are leaving traces for a future we will never see, feels too sad to say out loud. The universe does not forbid communication across the stars, it only forbids conversation. And the difference between those two things is the difference between everything. There was a time, not so long ago, when this distinction did not seem to matter, when the idea of listening to the stars felt like enough and the possibility of hearing a signal, any signal, seemed so extraordinary that the question of whether we could reply in time did not yet weigh on anyone. That time was the early 1960s, and the person at the centre of it was a young radio astronomer named Frank Drake. In April of 1960, Drake was 29 years old, and he had recently convinced his superiors at the National Radio Astronomy Observatory in Greenbank, West Virginia, to let him use one of their telescopes for a project that most of his colleagues thought was somewhere between visionary and absurd. He wanted to listen to two nearby stars, both of them roughly the same size and temperature as the Sun, and see if he could detect any radio signals coming from them that might have been produced by an intelligent civilization. The project had no official funding, no formal approval from any government agency, and no guarantee that it would detect anything at all. It cost about $2,000, most of which went toward building a simple receiver, and it was scheduled to run for a few months during the spring and summer, whenever the telescope was not being used for other observations. Drake called the project Ozma, after the princess in the Oz books, because, as he later said, the land of Oz was very far away, difficult to reach, and populated by strange and exotic beings. The two stars he chose to observe were Tau Ceti, about 12 light-years away, and Epsilon Eridani, about 11 light-years distant, both of them close enough that if anyone there had been transmitting a powerful radio signal in Earth's direction, the 85-foot dish at Greenbank might have been able to hear it. The observations were intermittent, a few hours at a time, spread across several months. The telescope was tuned to a frequency of 1420 MHz, the emission line of neutral hydrogen, a wavelength that Kirkonian and Morrison had proposed in a short paper published in Nature the previous year as a logical place for any civilization to broadcast. Their reasoning was elegant. Hydrogen is the most abundant element in the universe, and its emission at this frequency is one of the most fundamental markers in radio astronomy. Any civilization with radio telescopes would know about it, and so, they argued, if you wanted to send a message that might be noticed, you would send it at the one frequency that every astronomer in the galaxy would already be listening to, the way a traveller in a foreign country might shout in the lingua franca of the region, hoping that someone somewhere speaks the same language. Drake listened. He listened for hours, watching the signal strength rise and fall as the telescope tracked the stars across the sky, and for most of that time he heard nothing but the faint hiss of the cosmos, the background murmur of distant galaxies and ionized gas. But on the 8th of April, just a few days into the observations, something happened. The receiver picked up a strong rhythmic signal coming from the direction of Epsilon Eridani, a pattern of pulses, 8 per second, clear and regular and utterly unlike anything the telescope had been hearing before. Drake and his small team froze. For a moment no one said anything. They checked the equipment, checked the pointing, checked the frequency. The signal was still there, steady and insistent, and it was coming from the place in the sky where the star should be. It lasted for a few minutes, and then it vanished. They tried to find it again, swinging the telescope back to the same patch of sky, listening at the same frequency, but the signal did not return. Drake later learned that it had been interference from a classified military aircraft passing overhead. its radar transmitting at a frequency close enough to the hydrogen line that the receiver had picked it up. The false alarm was brief, and it was resolved quickly, but it left a strange residue of feeling, a mix of excitement and disappointment that was hard to shake, because for those few minutes it had felt real. It had felt like someone was speaking, and for the first time in human history we had been listening. The rest of Project Ozma found nothing. After about 150 hours of observation spread over 3 months, the telescope was quietly returned to its regular duties, and Drake moved on to other work. But the project had done something that no telescope had done before. It had turned a listening into a deliberate act, a planned search rather than an accidental discovery, and it had shown that such a search was technically possible, even if it required patience and modest resources and a willingness to hear nothing for a very long time. And it had also, quietly and without much fanfare, revealed the first outline of the problem that would come to define all searches for extraterrestrial intelligence. Even if someone had been transmitting from Tau Ceti or Epsilon Eridani, even if Drake had heard them clearly, the round-trip time for a message and a reply would have been at least 22 years. Drake was 29 when Project Ozma began. If he had detected a signal and immediately sent a reply, he would have been over 50 by the time the acknowledgement came back. His children, if he had any, would have been adults. The world would have moved on. And this was the closest case scenario, the nearest stars that seemed remotely plausible as homes for life. Farther out, the delays would be longer, measured not in decades but in centuries, and the idea that a conversation might unfold between two worlds across such distances began to look not merely difficult but conceptually incoherent, like trying to play chess by mail with someone who might be dead by the time your next move arrives. Drake understood this, in a theoretical sense, but in 1960 it did not yet feel like an obstacle. The mood of the time was optimistic, shaped by the conviction that the universe was large and old and probably full of civilizations, and that if we could just hear one of them, just once, it would be enough. The signal itself would be the revelation, the proof that we were not alone, and the question of whether we could have a conversation with them seemed at the time like a concern that could be addressed later, after the first contact had been made. Listening in that moment felt like the first step, the necessary beginning, and no one wanted to dwell too much on the shape of the second step, or the third, or the long and patient centuries that might be required to walk any farther. Cocconi and Morrison had written in their Nature paper that the probability of success was difficult to estimate, but that if we never searched, the chance of success was zero. It was a statement that carried a kind of quiet defiance, a refusal to be paralyzed by uncertainty, and it became, in the years that followed, one of the founding principles of the field. But what they did not say, and what no one said very much in those early years, was that even if the search succeeded, even if we heard a signal tomorrow, clear and unambiguous and full of information, the most likely outcome would not be a conversation but a recognition, a moment in which we understood that someone, somewhere, had once been alive and thinking and hoping that someone might hear them, and that by the time we heard them, they might already be gone, or changed, or so far removed in time from the moment of transmission that the message we received would be less like a greeting and more like an epitaph. The geometry was there from the beginning, written into the mathematics of light and distance, but it took a long time for anyone to say it plainly, because the truth was uncomfortable and the dream of contact was too precious to let go of, and for a while, listening felt like enough. The geometry was always there, written into the fabric of the universe itself, long before anyone on Earth began listening for signals from distant stars. It was codified in a paper published in the summer of 1905 in a German physics journal by a 26-year-old patent clerk working in Bern, who had never held an academic position and whose name was not yet known outside a small circle of correspondents. Albert Einstein called his paper on the electrodynamics of moving bodies, and buried within its dense mathematical arguments was a principle that would reshape not only physics, but the entire human understanding of what it means to look outward at the cosmos. The speed of light, Einstein argued, was not merely fast, it was absolute. It was the same for all observers, regardless of how they were moving, regardless of how the source of the light was moving, and nothing carrying information could ever exceed it. This was not a limitation of technology or engineering. It was a property of space-time itself, woven into the geometry of the universe at the most fundamental level, and no amount of cleverness or ambition or longing would ever change it. What Einstein had described, though it would take decades for the full implications to become clear, was a universe in which distance and time were not separate things but aspects of a single fabric, and in which the finite speed of light meant that every observation of a distant object was also inevitably an observation of the past. When you looked at the moon, you saw it as it had been a little more than a second ago. When you looked at the sun, you saw it as it had been about 8 minutes earlier. These delays were small enough to feel almost negligible, the kind of thing that mattered only to physicists and astronomers making precise measurements. But as the distances grew, the delays grew with them, and the universe began to reveal itself as a place where the present was always out of reach, where the farther you looked, the deeper into history you were gazing. Proxima Centauri, the nearest star to the Sun, sits a little over 4 light-years away, and the light arriving from it tonight left its surface more than 4 years ago. Whatever is happening there now, in this moment, is unknowable. The information has not yet had time to reach us. It is still crossing the void, travelling at the fastest speed the universe permits, and it will not arrive for years to come. The star we see in our telescopes is not the star as it is, but the star as it was, a ghost of its former self. And this is true of every object beyond our own small world. The centre of our galaxy, the dense core of stars and gas surrounding the supermassive black hole, astronomers have learned to call Sagittarius A star, lies roughly 26,000 light-years from Earth, and the light reaching us from that region tonight began its journey when the last ice age was ending, and the first permanent human settlements were being built in the fertile valleys of the Near East. The galactic centre we observe is not the galactic centre of today. It is the galactic centre of the late Pleistocene, and whatever has happened there since, whatever stars have been born or died, whatever civilisations might have risen or fallen in that crowded heart of the Milky Way, remains hidden from us, locked behind a wall of time that will not begin to lift for another 26,000 years. And the Andromeda Galaxy, the nearest large spiral to our own, the great wheel of light visible on clear autumn nights as a faint smudge in the constellation that bears its name, sits roughly 2.5 million light-years distant. The photons striking the mirrors of our telescopes tonight, the ones that form the images we study and admire, left Andromeda when the genus Homo was just beginning to emerge on the plains of East Africa, when the first stone tools were being shaped by hands that were not quite human, when the ancestors of everyone who would ever live were still learning to walk upright and had not yet discovered fire. That is the Andromeda we see. The Andromeda of now, the Andromeda of this present moment, is as inaccessible to us as the future, separated by a gulf of time so vast that it makes the span of recorded human history seem like the blink of an eye. This is what Einstein's principle means when you follow it to its conclusion. The universe is not a place where events happen simultaneously and we simply learn about them at different speeds. It is a place where the very concept of simultaneity breaks down across large distances, where the present is a local phenomenon confined to the immediate neighbourhood of the observer, and where everything beyond that neighbourhood exists only as history, preserved in the light that has finally completed its long journey. A telescope is not a window onto the cosmos as it is. It is a time machine, always showing us the past, and the farther it looks, the deeper into the past it sees. For the question of interstellar communication, this geometry carries a weight that is difficult to overstate. When Frank Drake pointed his radio telescope at Tau Ceti and Epsilon Eridani in 1960, he was not listening to those stars as they were in that moment, He was listening to them as they had been more than a decade earlier, and any signal he might have detected would have been a signal sent by beings who had no way of knowing, when they sent it, whether anyone on Earth would ever be listening, or whether the Earth of that future moment would even still be home to a civilization capable of hearing. And if Drake had heard something, and if he had immediately transmitted a reply, that reply would not have arrived at its destination for another 11 or 12 years, and any response to his response would not have reached Earth until the late 1980s, by which time the world would have changed in ways no one could have predicted. The conversation, if you could call it that, would have been stretched across decades, each exchange separated by a silence long enough for children to be born and grow to adulthood, for governments to rise and fall, for the very meaning of the original message to shift and fade in the memories of those who had sent it. And Tau Ceti and Epsilon Eridani were the nearest plausible targets. Farther out, the delays would be longer, measured not in years but in centuries, and the structure of any exchange would begin to resemble something less like a conversation and more like the slow accumulation of artifacts, messages sent into the void by one generation and received, if at all, by another that had no memory of the sending. The Arecibo message, transmitted in 1974 toward the globular cluster Messier 13, was aimed at a target so distant that the round-trip time for a reply would be 50,000 years. The people who composed that message, who encoded the human figure and the double helix and the schematic of the solar system into a stream of radio pulses lasting less than 3 minutes, knew that they would never hear an answer. Their children would never hear an answer. Their civilization, in any recognizable form, would almost certainly be gone by the time the light from Messier 13 had a chance to carry a response back to Earth. The message was not the beginning of a dialogue, it was a statement, a declaration, a kind of cosmic graffiti left on the wall of the universe by a species that wanted, more than anything, to be remembered. This is the truth that the geometry of space-time enforces on every attempt at interstellar communication. The speed of light is not merely a limit on how fast information can travel. It is a limit on what kind of relationship two distant civilizations can ever have. If they are close enough, within a few light years of each other, they might manage something resembling a slow correspondence, an exchange of messages that takes decades but remains within the span of a single human lifetime. If they are farther apart, the exchange stretches across generations, and the participants on each end become not individuals but institutions, cultures, perhaps entire species, handing the conversation down like an heirloom, hoping that someone in the future will still care enough to listen. And if they're very far apart, separated by thousands or millions of light years, the exchange becomes something else entirely, not a conversation, but a kind of archaeology, each civilization receiving messages from the deep past of the other and sending replies that will not arrive until the deep future, long after the senders have become dust and their world has moved on to concerns they could never have imagined. The silence of the universe, the absence of clear signals from other civilizations, is often treated as a mystery, a puzzle to be solved, a question demanding an answer. But the geometry of space-time suggests a different interpretation. The silence may not be an absence. It may be the natural state of a cosmos in which the speed of light is finite, in which every civilization is trapped in its own bubble of the present, able to send messages outward but unable to know whether anyone will ever receive them, unable to wait for a reply, unable to participate in anything resembling the back-and-forth exchange that we, as social creatures, instinctively imagine when we think about communication. The universe may be full of voices, each one calling out into the dark, and the reason we do not hear them may be simply that they are too far away, their messages still crossing the void, or already past us, or aimed in directions we have not yet thought to look. The geometry does not forbid the existence of other minds. It forbids the possibility of knowing them in the way we know each other, as partners in a shared present, as participants in a living conversation. It enforces with the cold precision of mathematics a kind of solitude that no technology can overcome. And yet knowing all of this, knowing the delays and the distances and the fundamental impossibility of anything resembling a real-time exchange, the people of Earth have still sent messages outward, not in the expectation of receiving a reply, but for reasons that are harder to articulate and perhaps more profound. In the early 1970s, as the first spacecraft designed to leave the solar system were being prepared for launch, a small group of scientists and artists began to think about what those spacecraft might carry, not for the benefit of any mission objective, but for the benefit of whoever might find them, someday, in the unimaginable future when they had drifted far enough from the sun to enter the space between the stars. Pioneer 10 launched on the 3rd of March 1972, the first spacecraft ever designed to travel beyond the asteroid belt and visit the outer planets. It was a small machine, about the size of a grand piano, powered by a nuclear generator and equipped with instruments to study Jupiter and the environment of deep space. But attached to its antenna support struts, shielded from the erosion of interstellar dust, was something that had nothing to do with the mission's scientific objectives. It was a plaque, about 6 inches by 9 inches, made of gold anodized aluminum, and it carried a message intended not for anyone on Earth, but for whoever might find the spacecraft after it had left the solar system and drifted into the galaxy. The plaque was the idea of a science journalist named Eric Burgess, who had suggested to Carl Sagan that the spacecraft ought to carry some indication of where it came from and who had built it. Sagan, already well known as a popularizer of astronomy and a passionate advocate for the search for extraterrestrial intelligence, embraced the idea and enlisted Frank Drake, the same Frank Drake who had conducted Project Ozma 12 years earlier, to help design the message. The artwork was created by Linda Salzman Sagan, Carl's wife at the time, and the result was a small golden rectangle bearing a diagram of the solar system, a schematic showing the spacecraft's trajectory past Jupiter, and most strikingly a pair of nude human figures, a man and a woman standing beside a silhouette of the spacecraft for scale. The man's hand was raised in a gesture of greeting, and above the figures was a diagram showing the position of the sun relative to 14 pulsars, a kind of cosmic map that might allow a finder to determine where the spacecraft had come from. Pioneer 11, launched a year later in April of 1973, carried an identical plaque. Both spacecraft completed their missions to Jupiter, and Pioneer 11 went on to visit Saturn, and then they continued outward, their instruments gradually failing, their power supplies slowly diminishing, until they fell silent and became drifters, cold and quiet, carried by their own momentum into the space between the stars. Pioneer 10 is now heading in the general direction of the star Aldebaran, the bright red eye of the constellation Taurus, and at its current speed it will take roughly 2 million years to reach that vicinity. Pioneer 11 is heading toward the constellation Aquila, and its journey to the nearest star in that direction will take even longer, perhaps 4 million years. The plaques they carry are not messages in any practical sense. They are artifacts, relics, time capsules launched into a future so distant that the word future begins to lose its meaning. And then came the Voyagers. In the summer of 1977, 2 spacecraft launched from Cape Canaveral within 16 days of each other, bound for a grand tour of the outer planets that would take advantage of a rare alignment occurring only once every 175 years. Voyager 2 launched first on the 20th of August, followed by Voyager 1 on the 5th of September. Both spacecraft were larger and more sophisticated than the Pioneers, and both carried a message far more elaborate than the simple plaques that had gone before. The message was a phonograph record 12 inches in diameter, made of gold-plated copper and encased in an aluminum jacket. On its surface were encoded 115 images, a selection of natural sounds including surf and wind and thunder and the calls of animals, musical selections from cultures around the world, and spoken greetings in 55 languages, ranging from ancient Sumerian to modern Mandarin. The record was curated by a committee chaired by Carl Sagan, with Frank Drake serving as technical director, Anne Druyan as creative director, Timothy Ferris as producer, and John Lomberg overseeing the visual content. Linda Salzman Sagan coordinated the spoken greetings. The entire production was completed in about 6 weeks, on a budget of roughly $1,500, and the result was one of the most ambitious attempts in human history to communicate with beings who might not share any of our languages, our biology, or our assumptions about the universe. The record bore an inscription, engraved on its surface in a place where it might be read by anyone who found it. The inscription read simply, "To the makers of music, all worlds, all times." It was a dedication, a hope, a statement of faith that somewhere, in the vast reaches of the galaxy, there might be others who understood what music was and why it mattered, and that the record might someday reach them, even if the people who made it were long gone. Sagan himself understood the improbability of the record ever being found. He wrote later that the spacecraft would be encountered and the record played only if there were advanced spacefaring civilizations in interstellar space, but that the launching of this bottle into the cosmic ocean said something very hopeful about life on this planet. The metaphor was apt. A bottle thrown into the sea has no expectation of being found, no reasonable hope of reaching any particular shore, and yet people have been throwing them for centuries. Driven by something deeper than probability, some need to send a part of themselves outward into the unknown and trust that it might, against all odds, be received. The Voyager spacecraft are still travelling outward, still crossing the boundary between the solar system and interstellar space. Voyager 1, as of this telling, is roughly 15.5 billion miles from Earth, farther than any human-made object has ever travelled, and it is approaching a milestone that will occur in the autumn of 2026, when it will reach a distance of 1 light day from the Sun, meaning that a signal sent from Earth will take a full 24 hours to reach it. At its current speed, Voyager 1 would take roughly 75,000 years to cover the 4.25 light years to Proxima Centauri, though it is not heading in that direction. Neither Voyager is aimed at any particular star. They are simply moving outward, following the trajectories imparted to them by their encounters with the giant planets, and they will drift through the galaxy for millions of years, perhaps billions, long after the Sun has exhausted its fuel and the Earth has become uninhabitable. The records they carry are not greetings in the sense that the Arecibo message was a greeting. They are not the opening line of a conversation. They are something closer to a will, a testament, a final statement by a species that knew it might not last forever and wanted to leave something behind, some evidence that it had existed, that it had wondered about the universe, that it had made music and fallen in love and looked up at the stars and hoped that someone, somewhere, might be looking back. The people who made the records knew they would never hear a reply. They knew their children would never hear a reply. They knew that by the time the records reached any star system where they might conceivably be found, the civilization that had created them would be unrecognizably different, or gone entirely, replaced by descendants who might not even remember that the records had been sent. And they sent them anyway, not because they expected an answer, but because the sending itself was the point, the act of reaching out, the refusal to accept that the geometry of the universe condemned them to silence. The story of interstellar communication, then, is not really a story about conversation at all. It is a story about legacy, about the things we send into the future without any hope of knowing whether they will be received, about the messages we write for readers who may never exist, in languages they may never understand, trusting that the act of sending is itself a kind of meaning. The plaques and the records are not so different in the end from the cave paintings at Lascaux or the cuneiform tablets of ancient Sumer, artifacts left behind by people who could not have imagined who would find them or what they would make of what they found. The difference is only one of scale. The cave painters were speaking to the future of their own species. The makers of the golden records were speaking to the future of the galaxy, and they knew with a clarity that the cave painters could never have possessed that the future they were speaking to was so distant that the word future itself became a kind of abstraction, a placeholder for something beyond human comprehension. And yet the records exist. The plaques exist. the Arecibo message travelling at the speed of light toward a cluster of stars that will have moved by the time it arrives, exists. These are not the beginnings of conversations. They are the endings of them, the final words spoken by a species that wanted more than anything to be heard. Even if no one was listening, even if the geometry of the universe made listening impossible, even if the only audience for the message was the message itself, drifting through the dark, carrying the memory of a world that had once been home to creatures who looked up at the night sky and wondered whether they were alone. And perhaps the deepest irony is that the very era in which humanity began to send those messages, the era in which we first possessed the technology to announce our presence to the cosmos, may turn out to have been a narrow window, a brief flicker in the long history of our species, during which we were for a short time conspicuous to anyone who might have been watching. Consider what happened to the Earth in the 20th century, considered from the perspective of a listener stationed very far away. For most of human history, our planet was electromagnetically silent. The radio spectrum above the atmosphere was empty. If some civilization on a world orbiting a nearby star had turned a sensitive receiver toward our solar system at any point before the late 19th century, they would have detected nothing but the natural hiss of the sun, the crackle of lightning in our atmosphere, the faint thermal glow of a rocky world at a comfortable distance from its parent star. There would have been no way to distinguish Earth from any other lifeless planet in the galaxy. We were invisible, not because we were hiding, but because we had not yet learned to make the kind of noise that travels between stars. That changed gradually at first in the early years of the 20th century. The first experimental radio transmissions were weak and local, designed to cross a few miles of farmland or the width of a city, and they dissipated into meaningless static long before they left the atmosphere. But as the technology improved, as transmitters grew more powerful and broadcast towers rose higher, some fraction of that energy began to escape into space, radiating outward at the speed of light, carrying with it the faint signature of a technological civilization. By the middle of the century, the Earth had become, for the first time in its 4.5 billion year history, a source of artificial radio emissions detectable from interstellar distances. The radio bubble, as it is sometimes called, is the expanding sphere of space that contains our unintentional leakage, the accumulated broadcast of more than a century of radio and television, and radar, spreading outward in all directions at 300,000 kilometers per second. The oldest signals in that bubble are now more than 100 light-years from Earth, which means they have reached the vicinity of several thousand stars, any of which might conceivably harbour planets, any of which might conceivably harbour listeners. The bubble is still growing, adding another light-year to its radius with every passing year, encompassing more and more of the local stellar neighbourhood, announcing our presence to an ever larger audience. But the bubble is not getting brighter. In fact, by some measures, it is getting dimmer. The strongest radio signals that Earth has ever produced were not the deliberate messages sent to the stars, not the Arecibo transmission, or the handful of other intentional broadcasts that have been aimed at specific targets over the years. The strongest signals were the ones we never meant to send at all, the powerful radar installations built for military and aviation purposes, the high-energy pulses designed to track aircraft and map the surfaces of nearby planets, and, for a time, the concentrated beams of analog television transmitters, which poured enormous amounts of energy into the sky in order to deliver entertainment to millions of homes. At its peak, the combined radio output of the Earth was substantial enough that a sufficiently sensitive receiver, positioned within a few dozen light-years, might have been able to detect it, might have been able to notice that something unusual was happening around this particular yellow star, something that did not fit the pattern of natural radio sources, something that suggested the presence of technology. But that peak has passed. The technologies that made us most visible are being replaced by technologies that make us nearly invisible. Analog television, which broadcast on frequencies that penetrated the atmosphere and radiated into space, has given way to digital broadcasting and cable and streaming services, which use far less power, and keep most of their energy confined to the ground. International communications, which once relied on powerful ground-based transmitters, bouncing signals off the ionosphere or beaming them towards satellites, now travel primarily through fibre optic cables, which do not leak into space at all. The radar installations remain, and they are still among the most detectable signatures of our civilization, but they are increasingly supplemented by satellite-based systems which direct their energy downward rather than outward. The Earth, having spent a few decades shouting into the void, is learning to whisper. This is not a deliberate choice. No one decided that humanity should become quieter to avoid detection by potential observers. It is simply the natural evolution of communication technology, the relentless pursuit of efficiency, the replacement of wasteful systems with systems that use less energy and deliver better results. The same process that made us briefly visible is now making us progressively less so. A civilization observing the Earth from 100 light-years away would see our signals arriving now, more than a century after they were sent, and they would see them growing stronger with each passing year, the record of our technological adolescence unfolding in slow motion. But if they continued to watch, if they tracked our output decade by decade as the light continued to arrive, they would eventually see the signals begin to fade, not because we'd been destroyed, but because we'd moved on to better methods, methods that do not announce themselves to the universe. The window of visibility, then, is not a permanent feature of a technological civilization. It is a phase, a transitional period between the development of radio technology and the development of more efficient alternatives. How long that window lasts depends on the particular trajectory of each civilization's technological evolution, but there is no reason to assume it lasts forever, and there is some reason to think it might be surprisingly brief. A few centuries, perhaps, a few decades in some scenarios, a flicker of light in the long darkness of a planet's history, easily missed by anyone who was not watching at precisely the right moment. And this is the difficulty that haunts every attempt to estimate our chances of making contact with another intelligence. It is not enough for two civilizations to exist in the same galaxy. It is not even enough for them to exist at the same time in the sense of overlapping within the same few million years. They must also exist in the same technological phase, the phase in which they are capable of producing detectable signals and actively listening for them, and that phase must overlap in time, and the signals from each must have had time to cross the intervening distance, and each must be looking in approximately the right direction, at approximately the right frequency, at approximately the right moment. The problem is not just distance. The problem is the intersection of two narrow windows, two brief eras of visibility, in a galaxy where the distances are measured in decades and centuries and millennia of travel time for light. This is the context in which Frank Drake, more than 60 years ago, tried to think systematically about the question of how many detectable civilizations might exist in the Milky Way. He had already conducted his search of Tau Ceti and Epsilon Eridani, the two nearby stars he observed in the spring of 1960, using equipment borrowed and improvised and funded on a shoestring. He had listened for roughly 150 hours and heard nothing but interference. The silence had not surprised him exactly, but it had clarified the problem. The question was not whether intelligent life existed elsewhere in the galaxy. The question was whether it existed in a form that could be detected, and whether it existed now, and whether now meant the same thing when you were talking about civilizations separated by distances that light itself took years or decades or centuries to cross. In the autumn of 1961, a small group gathered at the National Radio Astronomy Observatory in Greenbank, West Virginia, the same facility where Drake had conducted his search the year before. The meeting was informal, almost private, a gathering of perhaps a dozen scientists from various disciplines, brought together to discuss a question that had never before been the subject of a serious scientific conference. Among the attendees was Carl Sagan, then a young planetary scientist, and Melvin Calvin, a chemist who had learned during the conference that he had been awarded the Nobel Prize for his work on photosynthesis. There were astronomers and biologists and engineers, people who had been thinking about the question of extraterrestrial intelligence from different angles, and they had come together to try to organise their thinking, to break the problem down into pieces that might be addressed one at a time. Drake, as the organiser, had prepared an agenda, and the agenda took the form of a simple equation. It was not an equation in the usual scientific sense, not a relationship derived from physical law or tested against experimental data. It was more like a framework, a way of identifying the factors that would need to be understood before anyone could make a meaningful estimate of the number of detectable civilizations in the galaxy. The equation multiplied together a series of terms, each representing a different piece of the puzzle, from the rate at which new stars form in the galaxy to the fraction of those stars that have planets, from the fraction of planets that develop life to the fraction of life that develops intelligence, from the fraction of intelligent species that develop technology capable of interstellar communication to the length of time such civilizations remain detectable. The equation was elegant in its way. It organized the problem beautifully. It allowed the scientists at Green Bank to focus their discussion on specific questions, to identify where the uncertainties were greatest, to separate the factors that were becoming measurable from the factors that remained entirely unknown. The attendees, who would later refer to themselves half-jokingly as the Order of the Dolphin, in honour of one participant's research into dolphin communication, spent 3 days working through the terms, estimating where they could, acknowledging ignorance where they could not. But there was one term in the equation that dominated all the others, one variable that swallowed every other uncertainty and made the final answer almost entirely unknowable. It was the last term, the one Drake had labelled L, and it stood for the average lifetime of a communicative civilization, the number of years during which a society remains capable of producing and detecting interstellar signals. Every other term in the equation was, at least in principle, a question about the universe, a question that could someday be answered by observation and measurement. How many stars form each year? Astronomers could estimate that. How many stars have planets? The search was already beginning, and within a few decades it would yield thousands of confirmed discoveries. How many planets have conditions suitable for life? Uncertain, but not beyond the reach of future science. How often does life arise? How often does it become intelligent? How often does it develop technology? Difficult questions, but questions about the natural world. Questions that might eventually yield patient investigation. But L was different. L was not a question about the universe. L was a question about ourselves, about the durability of civilizations, about the tendency of intelligent species to survive their own technological adolescence, or to destroy themselves with the very tools that made them detectable. L was a question about nuclear weapons and climate change and resource depletion and pandemics, about all the ways a civilization might end, deliberately or accidentally, before it had existed long enough to make contact with anyone else. And L was also a question about technological evolution, about the tendency of communicative methods to become more efficient and less detectable over time, about the window of visibility that might open briefly and then close again, leaving a civilization still alive but effectively silent. If L is large, if civilizations typically survive for millions of years and remain detectable throughout, then the galaxy could be full of signals, and our failure to detect them would be a puzzle demanding explanation. But if L is small, if civilizations typically flicker into visibility for a few centuries and then fade, either through self-destruction or through technological evolution, then the galaxy could have hosted billions of intelligent species over its long history and still contain almost none that are detectable at any given moment. The question of how many civilizations exist becomes, in this formulation, a question of how many exist right now, and right now is a concept that stretches and distorts across interstellar distances, where the light from a nearby star carries news that is already years out of date, and the light from a more distant star carries news that is decades or centuries or millennia old. The Fermi paradox, the famous question attributed to the physicist Enrico Fermi, who supposedly asked over lunch one day why, if the galaxy was full of intelligent civilizations none of them had made their presence known, is usually framed as a question about space, about the emptiness of the heavens, about the absence of evidence for beings who should by some calculations be everywhere. But the Drake equation, and particularly its final term, reframes the paradox as a question about time. The question is not so much where is everybody as when were they? A galaxy that has been producing intelligent civilizations for billions of years might still be profoundly lonely at any given moment, if those civilizations tend to exist only briefly, their windows of visibility opening and closing like fireflies in a vast and ancient forest, each flash too short and too far from the others to ever be seen. And so the hope arises naturally that technology might solve the problem, that better instruments and faster ships might narrow the gap, might turn the impossible into the merely difficult, might allow two civilizations separated by the geometry of the universe to hold something resembling a conversation. The instruments have certainly improved. The 500-meter aperture spherical telescope, built into a natural depression in the mountains of Guizhou province in China, is the largest single-dish radio telescope ever constructed, a vast bowl of aluminum panels that can be shaped and reshaped to track objects across the sky. It began formal operations in early 2020, and its sensitivity exceeds anything that came before it, capable of detecting fainter signals from greater distances, capable of surveying more of the sky in less time. Optical telescopes have been joined by instruments designed to detect laser pulses, brief flashes of coherent light that might be easier to produce and easier to detect than radio waves, and that might offer higher bandwidth, more information packed into each signal. The search for extraterrestrial intelligence has expanded from a handful of dedicated projects to a broader effort involving researchers around the world, funded in part by private initiatives, supported by computing power that would have been unimaginable to the scientists who gathered at Greenbank in 1961. And the dream of sending not just signals but physical messengers has taken on new urgency. In 2016, a project called Breakthrough Starshot was announced, backed by the physicist Stephen Hawking and the entrepreneur Yuri Milner, among others, with the goal of developing a new kind of interstellar probe. The concept was audacious. Rather than sending a conventional spacecraft, massive and slow, the project proposed to send a fleet of tiny probes, each weighing only a few grams, each equipped with a light sail that could be accelerated by a powerful laser beam fired from Earth. The lasers would push the sails to velocities far beyond anything achieved by chemical rockets, perhaps as much as 20% of the speed of light. At such speeds, a probe could reach the Alpha Centauri system in roughly 20 years, rather than the tens of thousands of years that would be required by current technology. The engineering challenges are enormous. Building a laser array powerful enough to accelerate a gram-scale probe to relativistic velocities would require advances in materials and optics and energy generation that do not yet exist. Keeping the probe on course, protecting it from the dust and radiation of interstellar space, communicating with it across the light years, all of these problems remain unsolved. But the concept is being studied seriously, and the ambition is real. The dream of sending something from Earth that could reach another star within a human lifetime, that could send back images and data from a world orbiting another sun. And yet even this dream, even the most optimistic scenario for interstellar travel, does not restore what the geometry of the universe has taken away. A probe travelling at 20% of the speed of light would reach Alpha Centauri in 2 decades, but the signals it sent back would still travel at the speed of light, no faster, and they would take more than 4 years to arrive. The probe could observe, could photograph, could perhaps even detect signs of life on a planet orbiting Proxima Centauri, but it could not hold a conversation with anything it found there. The round-trip time for a single exchange of messages would still be measured in years. And Alpha Centauri is the nearest star system to our own. For more distant targets, even the fastest conceivable probe would take centuries to arrive, and the signals it sent back would take additional centuries to return, the speed of a light is not a technological limitation. It is not a barrier that better engineering can overcome, a wall that future civilizations might learn to climb or tunnel through. It is woven into the structure of the universe itself, a fundamental feature of the geometry of space and time. Nothing that carries information can travel faster. No signal, no message, no probe, no ship, however advanced, can outrun light. The universe permits faster than light expansion of space itself, which is why distant galaxies are receding from us at velocities that exceed the speed of light, but it does not permit faster than light transmission of information or matter. The causal structure of the cosmos, the principle that effects cannot precede their causes, depends on this limit. To violate it would be to violate causality, to send messages into the past, to create paradoxes that would unravel the fabric of physics. Better telescopes allow us to hear fainter whispers from farther away. Faster probes allow us to shorten the time between sending a messenger and receiving whatever news it gathers. Laser communication allows us to pack more information into each pulse of light. But none of these advances, singly or together, restore simultaneity. None of them allow two civilizations, separated by dozens or hundreds or thousands of light years, to experience anything resembling real-time exchange. The delay is not an inconvenience to be minimized. It is a fundamental feature of the universe, as basic as the existence of space and time themselves. The geometry that separates the stars is not merely a matter of distance, it is a matter of enforced isolation, a structure that permits the sending of messages but forbids the holding of conversations, that allows civilizations to know of one another's existence perhaps, but not to share in one another's lives. The search continues, the telescopes listen, the probes are planned and designed and debated, and perhaps someday a signal will arrive, faint but unmistakable, carrying news of another intelligence somewhere in the vastness of the Milky Way. Proof that we are not alone, that the universe has produced, at least twice, creatures capable of wondering whether the universe had produced them. But even then, even in that moment of discovery, the nature of what has been found will remain bounded by the same constraints. A signal from a star 50 light-years away would carry news that was 50 years old when it arrived, and any reply we sent would take another 50 years to reach its destination. A century would pass between question and answer, between greeting and response. Generations would live and die in the interval. The civilization that sent the original message might no longer exist by the time our reply arrived. We might be responding to ghosts, to the echoes of a world that had fallen silent while our answer was still travelling through the dark. And so we arrive at a strange and melancholy corner of the physics, a place where the universe seems to offer an escape from its own constraints, only to reveal that the escape leads somewhere even lonelier than the prison it promised to unlock. The idea is simple enough to state, and it has been with us for more than a century, ever since a young patent clerk in Bern began to think carefully about what it would mean for the speed of a light to be the same for all observers. If time itself is not absolute, if it flows at different rates depending on how fast you're moving, then a traveller who leaves Earth at a substantial fraction of the speed of light will experience less time than the people left behind. The journey that takes decades or centuries by the reckoning of those who stayed home might feel like only a few years to the one who made the trip. The stars, which seemed impossibly far when measured in human lifetimes, might become reachable after all, not by making ships faster than light, which remains forbidden, but by making the subjective experience of the journey shorter for the traveller. The distance does not shrink in any absolute sense, and the light years do not become fewer, but the years that the traveller must endure while crossing them become compressed, folded, made bearable by the strange geometry of space-time at relativistic velocities. This is not speculation. It is not a theoretical curiosity that physicists discuss but have never observed. Time dilation is one of the most thoroughly verified predictions of modern physics, confirmed by experiments with particle accelerators, by observations of cosmic rays, by the behaviour of unstable particles that live longer when they are moving fast than when they are standing still. The clocks aboard satellites in orbit around Earth tick at a slightly different rate than clocks on the surface, and the global positioning system that guides ships and airplanes and automobiles must account for this difference, or its calculations would drift by kilometres per day. The effect is real, and it is measurable, and it has been measured over and over again with increasing precision for more than half a century. In the spring of 2015, an American astronaut named Scott Kelly began a mission that would keep him aboard the International Space Station for nearly a year. The station orbits Earth at a speed of roughly 17,500 miles per hour, completing a full circuit of the planet every 90 minutes, and Kelly remained aboard for 340 days. His twin brother, Mark Kelly, also an astronaut, remained on Earth. The two of them were genetically identical, born 6 minutes apart, and the mission offered an unprecedented opportunity to study what happens to a human body during long-duration spaceflight. Researchers examined their bones, their muscles, their immune systems, their gut bacteria, the expression of their genes. But there was another difference between the brothers, one that required no medical examination to understand, one that followed directly from the physics that Einstein had worked out more than a century earlier in his small apartment in Bern. When Scott Kelly returned to Earth in the spring of 2016, he was approximately 5 milliseconds younger than he would have been if he had stayed on the ground. His brother Mark, who had been 6 minutes older at birth, was now 6 minutes and 5 milliseconds older. The gap was tiny, far too small to notice in any practical sense, invisible to the naked eye, imperceptible to the body. But it was real. It had been measured. It was a direct consequence of the velocity at which Scott Kelly had been travelling, a velocity that, while impressive by human standards, was only a vanishing fraction of the speed of light. Mark Kelly, speaking at a conference in San Diego a few months after his brother's return, joked about the difference. He noted that whereas he used to be just 6 minutes older, now he was 6 minutes and 5 milliseconds older. He speculated with a grin that if 10 years from now he looked like he was 60 and his brother looked like he was 80, the audience would know what had happened. The joke landed because everyone in the room understood that 5 milliseconds was nothing, that no one would ever notice such a difference, that the effects of aging and environment and chance would swamp any relativistic contribution by many orders of magnitude. But the joke also carried within it a deeper truth, a truth that becomes less funny and more haunting as the velocities increase and the journeys lengthen. At orbital speeds, the effect is negligible. At a significant fraction of the speed of light, it becomes dramatic. A traveller moving at 90% of light speed would experience time passing at less than half the rate of someone who stayed behind. A journey that took a century by Earth's reckoning might feel like only a few decades to the one who made the trip. At 99% of the speed of light, the ratio becomes even more extreme. At 99.9%, more extreme still. The mathematics allows, in principle, for a traveller to cross vast distances while aging only a handful of years, while back home on Earth, centuries or millennia pass. The stars that seemed unreachable become reachable, not in the sense that the trip becomes short by the reckoning of those who wait, but in the sense that the traveller might survive to see the destination, might step out onto another world while still young enough to remember the one they left behind. And this is where the melancholy begins, where the apparent escape route reveals itself as something else entirely. The traveller who leaves Earth at relativistic speeds, who crosses the light years while aging only a few years, cannot send a message home any faster than light. The physics that allows time to flow slowly for the moving traveller does not allow information to outrun the photons that carry it. A message sent from the ship would travel at the speed of light, and it would take just as long to reach Earth as it would if time dilation did not exist at all. The traveller might arrive at a distant star after experiencing only 10 years of subjective time, but any signal sent back to Earth would still take decades or centuries to arrive, depending on the distance. And a message from Earth sent in reply would take just as long to reach the traveller. The compression of time that makes the journey survivable for the one who travels does nothing to shorten the wait for the ones who stayed behind. The traveller who returns home after a relativistic journey does not return to the world they left. They return to a world that has aged by the full amount of time that passed in its own reference frame. A world where everyone they knew has grown old or died, where the cities have changed, where the languages may have shifted, where the political borders and the cultural assumptions and the technologies have all moved on without them. The traveller has not escaped time. They have only experienced less of it than everyone else. They have traded one kind of isolation for another, exchanging the loneliness of being separated by distance for the loneliness of being separated by time, arriving in a future that no longer remembers them, that has no place waiting for them, that has become, in every meaningful sense, a foreign country. Consider what this means for any attempt to visit another civilization, to make contact not through the exchange of radio signals but through the physical presence of travellers who cross the void between the stars. Even if we developed ships capable of travelling at a substantial fraction of the speed of light, even if we found volunteers willing to make the journey, the travellers who arrived at another world would not be ambassadors from contemporary Earth. They would be emissaries from a vanished past, carrying memories and assumptions and cultural knowledge that might be centuries out of date by the time they arrived. And if they ever chose to return, they would come home to a world that had moved on without them, a world where their grandchildren's grandchildren might be dust, where the institutions that sent them might have collapsed or transformed beyond recognition, where the very meaning of the mission might have changed in ways that no one who planned it could have anticipated. The apparent escape from the constraint of distance becomes, on closer examination, a different kind of trap. Time dilation allows the stars to be reached within a human lifetime, but it does not allow the traveller to remain connected to the world they left behind. It does not allow them to return to a society that has not aged. It does not allow them to hold a conversation with anyone at home while they are travelling, because the messages still crawl at the speed of light, still take years or decades or centuries to arrive, still carry news that is already old by the time it is received. The traveller who reaches another civilization might shake hands with beings who have wondered about the universe, just as we have wondered, might learn things about the cosmos that no one on Earth has ever known, might experience wonders beyond imagining, but they cannot share those wonders with anyone at home in anything resembling real time. They cannot call back to say what they have found. They can only send messages that will arrive long after they were sent. Messages that might reach a world that has changed so much that no one remembers why the travellers left in the first place. And now we must widen the map further still, must step back from the scale of individual journeys and individual lifetimes, and look at the structure of the galaxy itself, the vast wheel of stars in which all of this unfolds. The Milky Way is a barred spiral galaxy, a great pinwheel of gas and dust and stars turning slowly in the darkness between the galaxies. Its disk is roughly 100,000 light-years across, which is to say that a beam of light, travelling at the fastest speed the universe allows, would take 100,000 years to cross from one edge to the other. The disk is thin compared to its width, only about 1,000 light-years from top to bottom in most places, but even that modest thickness is vast by any human standard. A gulf that would swallow entire civilizations without a trace. Our sun sits about 26,000 light-years from the galactic centre, roughly halfway out along one of the spiral arms, in a region that is neither particularly crowded nor particularly empty, a middle suburb of the cosmic city. And the galaxy is not standing still. The stars are moving, all of them, carried along by the rotation of the disk, by the gravitational pull of the hundreds of billions of other stars, by the dark matter that threads through the space between them and shapes the structure of the whole. Our sun travels at roughly 230 kilometers per second relative to the galactic centre, which sounds fast and is fast by any earthly standard, roughly 500,000 miles per hour, but which is still only a tiny fraction of the speed of light. At this velocity, the Sun takes approximately 225 to 250 million years to complete a single orbit around the galaxy, a span of time so long that it swallows entire geological eras, entire chapters of the history of life on Earth. The last time the Sun was in this part of its orbit, dinosaurs had not yet appeared. The next time it returns to this position, whatever lives on Earth, if anything still does, will be as different from us as we are from the single-celled organisms that drifted in the ancient seas. Every other star in the galaxy is moving too, each on its own orbit, each at its own velocity, each drifting slowly relative to its neighbours over timescales that dwarf any human endeavour. A civilization that sends a signal toward a nearby star is not sending it toward a fixed point in space. It is sending it toward a target that is moving, that will have shifted position by the time the signal arrives, that will have shifted further still by the time any reply could return. The distances involved are so vast and the travel times so long that the motion of the stars becomes significant, becomes something that must be accounted for, becomes yet another layer of complication in any attempt to exchange messages across the void. And these signals themselves, the radio waves and the laser pulses and whatever other forms of electromagnetic radiation a civilization might use to make itself known, do not travel as focused beams that maintain their strength across unlimited distances. They spread as they travel, expanding in spherical shells that grow larger and weaker with every passing moment. The intensity of a signal falls off with the square of the distance from its source, which means that a signal that has travelled twice as far is not half as strong but 1/4 as strong, and a signal that has travelled 10 times as far is not 1/10 as strong but 1/100th. By the time a signal has crossed 1,000 light years, it has spread across a sphere so vast that the energy reaching any particular point is vanishingly small, a whisper so faint that it might be indistinguishable from the background noise of the cosmos, from the radio hum of the galaxy itself, from the static left over from the birth of the universe. A civilization that broadcasts a signal in all directions, an omnidirectional transmission meant to announce its presence to anyone who might be listening, is fighting against this geometry, spreading its energy across an ever-expanding sphere, diluting its message until it becomes almost impossible to detect. A civilization that focuses its transmission into a narrow beam, aiming at a specific star or a specific region of the sky, can concentrate its energy and make its signal stronger at the intended destination. But it must know where to aim, must choose which stars to target out of the hundreds of billions in the galaxy, must guess which directions are worth the effort, and accept that signals sent in other directions will never be sent at all, and even a focused beam, aimed carefully at a specific star, is aiming at a moving target. The star that receives the signal will not be in the same position when it sends a reply. The original sender will have moved as well, drifting along its own galactic orbit, shifting position by a measurable amount over the decades or centuries that pass between transmission and response. A reply aimed at where the sender was when the original signal was sent would miss entirely, would pass through empty space where the sender used to be, would continue on into the darkness without ever reaching anyone. A reply aimed at where the sender will be when the reply arrives requires a prediction, a calculation, an estimate of how far and in what direction the sender will have moved during the transit time of the signal. Over short distances and short timescales, such predictions are straightforward. Over longer distances and longer timescales, the uncertainties accumulate, the errors compound, the chance of missing the target grows. The galaxy, seen from this perspective, is not a place where civilizations might meet and converse, not a cosmic forum where ideas are exchanged and relationships are built across the light years. It is a place where signals pass through one another in the dark, where transmissions that were sent with hope and care arrive at destinations that may no longer be listening, where replies are sent toward coordinates that are already out of date, where the motion of the stars and the expansion of the signals and the finite speed of light conspire to make every exchange an act of faith, a message thrown into the void with no guarantee that it will ever be received, much less answered. Consider a civilization on the far side of the galaxy, 70 or 80,000 light years away, A signal from that civilization would take 70 or 80,000 years to reach us, carrying news of a world that existed when our ancestors were painting on cave walls, when the glaciers of the last ice age still covered much of the northern continents. And a reply from us would take another 70 or 80,000 years to reach them, arriving at a world that would have changed beyond recognition, that might have risen to heights we cannot imagine or fallen into silence long before our answer arrived. The round-trip time for a single exchange would be longer than the entire span of recorded human history, longer than the time since the first cities were built, longer than the time since the invention of writing. Whatever question they asked would be answered by beings so far removed from the askers that the answer might no longer make sense, might refer to concepts and concerns that had long since ceased to matter, might arrive at a world where no one remembered that the question had ever been posed. And this is not the worst case. This is merely the far side of a single galaxy, a distance that is large by human standards, but small by the standards of the universe as a whole. The nearest large galaxy to our own, the Andromeda Galaxy, is more than 2 million light-year away, and the light we see from it tonight left its stars before there were human beings on Earth, before there were primates, before there were mammals, before there were dinosaurs. A signal sent to Andromeda would take more than 2 million years to arrive, and a reply would take more than 2 million years to return. The civilizations that might exist in that distant galaxy are separated from us not merely by distance, but by time, by spans so vast that the very concept of conversation loses all meaning, that the very idea of exchange becomes an abstraction, a gesture toward connection that can never be consummated. The geometry of the universe is not neutral. It is not a blank canvas on which civilizations might paint whatever relationships they choose. It is a structure that imposes constraints, that enforces separations, that permits the sending of messages but forbids the holding of conversations, that allows the existence of other minds but denies the possibility of sharing lives with them. The silence that fills the space between the stars is not necessarily the silence of absence, not necessarily proof that we are alone. It might be the silence of geometry, the enforced solitude of a cosmos in which every civilization, no matter how advanced, no matter how curious, no matter how eager to reach out and touch another mind, is trapped within its own bubble of causality, able to send but not to converse, able to transmit but not to connect. The broadcasts that we have sent, the signals that have leaked from our world and spread outward in an expanding shell, are moving through a galaxy where nothing stands still, where the stars themselves are drifting on their long orbits, where any civilization that might receive our messages will have moved by the time they arrive, and will have moved further still by the time any reply could reach us. The signals that others might have sent are passing through our neighborhood even now, perhaps, whispers from worlds that no longer exist, greetings from civilizations that fell silent while their messages were still traveling, questions that will never be answered because the askers are already gone. The galaxy is full of crossing paths, of signals that were sent with hope and received by no one, of messages that arrived at destinations where no one was listening, of broadcasts that weakened and spread and faded into the background noise of the cosmos. The field of stars that seemed, from a distance, like a place where minds might meet and share their understanding of the universe reveals itself, on closer examination, as a field of solitudes, a vast and beautiful isolation in which each civilization, if civilizations exist at all, must make its own meaning, must ask its own questions, must come to terms with the possibility that the answers, if answers exist, will arrive too late to matter, will come from worlds too far away to touch, will be spoken in languages that no one alive will ever learn to read. And yet the mind that grasps this isolation does not simply accept it. The same restlessness that once led human beings to build rafts and cross oceans, to chart the stars and name the constellations, to aim radio telescopes at distant suns and listen for patterns in the static, that same restlessness turns, inevitably, to the question of whether there might be some way around the constraint, some architecture of connection that could bridge the unbridgeable, some network of patience and engineering that could transform the galaxy from a field of solitudes into something more like a community. The idea is older than most people realize, and it emerged not from optimism but from a sober reckoning with the mathematics of light. In the early 1960s, when the first radio searches for extraterrestrial intelligence were still fresh, and the silence had not yet accumulated its weight of decades, an Australian physicist named Ronald Bracewell sat down to think through the problem from first principles. He was not a dreamer. He was a radio astronomer, trained in the hard discipline of extracting faint signals from the noise of the cosmos, and he understood better than most how unforgiving the distances were. A civilization on a world orbiting a star 12 light-years away could send a signal to Earth, and Earth could send a reply, but the conversation would unfold across decades. Every question would wait more than 20 years for an answer. Every clarification, every follow-up, every attempt to build on what had been learned would face the same punishing delay. By the time a dialogue had developed any depth at all, generations would have passed on both ends, and the people conducting it would be the grandchildren and great-grandchildren of those who had begun it. Bracewell's insight, published in the journal Nature in 1960, was that there might be another way. Instead of sending signals across the light years and waiting for replies, a civilization might send something else, something more patient, something capable of waiting at the destination until the time was right. The something he had in mind was a probe, a robotic spacecraft carrying enough intelligence to conduct a conversation on its own, to monitor a star system for signs of technological life, and to establish contact when such life appeared. The probe would be dispatched long in advance, perhaps thousands of years before contact was expected, and it would wait in silence until the target civilization reached the stage where it could be detected, where it was ready to receive a greeting. The mathematics of such a probe are elegant in a melancholy way. The probe itself would travel slowly, perhaps at a fraction of a percent of the speed of light, taking centuries or millennia to reach its destination. But once it arrived, it would be there, present, local, able to conduct a dialogue without the punishing delays of interstellar communication. A message sent from the probe to a planet in the same solar system might take minutes or hours, not years or decades. The conversation could unfold in something like real time, could build depth and nuance, could respond to questions and answer them while the questions were still fresh. The probe would be an ambassador, a representative, a patient watcher dispatched across the void to serve as a local presence where no local presence could otherwise exist. Bracewell himself suggested, with a scientist's careful sense of possibility, that such probes might already be here, drifting somewhere in our own solar system, waiting for us to reach the point where we could notice them, where we could receive their greeting and understand what it meant. He was not proposing that this was likely, only that it was not impossible, that the mathematics permitted it, that a civilization older and more patient than ours might have chosen this path, rather than the endless frustration of shouting across the light years and waiting for answers that would arrive after everyone who asked the questions was dead. The idea has lingered in the literature of the field ever since, returning again and again in papers and speculations, acquiring the name of its originator. A Bracewell probe is any autonomous spacecraft dispatched to another star system to serve as a local ambassador, to monitor for intelligence, to initiate contact when the time is right. The concept has found its way into fiction, into the lunar monolith of Arthur Clarke's imagination, into the patient watchers of a dozen other stories, but it remains grounded in a sober understanding of what the geometry of the universe permits and what it denies. And the denial is the heart of the matter. Even the most sophisticated Bracewell probe, the most patient and intelligent robotic ambassador, cannot overcome the fundamental constraint. It can conduct a dialogue with a local civilization. It can answer questions, receive replies, build a relationship that spans decades instead of centuries, but it cannot connect the two civilizations themselves. The probe is a representative, not a bridge. The conversations it conducts are between itself and whatever minds it finds, not between its creators and those minds. The civilization that dispatched the probe remains separated from the civilization that receives it by the same unbridgeable gulf of light years and time. They cannot share a moment. They cannot exchange ideas in real time. They cannot learn what the other is thinking now, only what the other was thinking when the probe was launched, only what messages the probe carries from an era that may already be ancient history by the time the dialogue begins. Later, thinkers extended the idea, imagining not just single probes but networks, vast constellations of relay stations scattered across the galaxy, each one capable of receiving signals from its neighbours, storing them, forwarding them onward, amplifying them for the next leg of the journey. The physicist Geoffrey Landis has explored such architectures, tracing out the engineering requirements, the power demands, the maintenance needs, the protocols that would be necessary to ensure that messages survive the journey from one node to the next without degrading into noise. Modern research into what is called delay-tolerant networking, developed partly for missions within our own solar system where signals can take minutes or hours to arrive, has provided tools for thinking about how such a system might work, how data might be stored at each node until the next node acknowledges receipt, how custody might be transferred across distances that make real-time handshakes impossible. The picture that emerges from this work is haunting in its implications. It is possible in principle to build a network that spans the galaxy, a system of relays that could carry messages from one end of the Milky Way to the other, that could preserve knowledge across distances of 100,000 light years, that could serve as a kind of infrastructure for a galactic civilization. But the network, no matter how sophisticated, would not be a communication system in any sense that we would recognize. It would be a library, a repository, a place where knowledge was stored and forwarded but never shared in the moment of its creation. The messages that travelled through such a network would be letters to the future, archives for minds not yet born, transmissions from civilizations that might already be gone by the time their words arrived at their destinations. The relays themselves might be staffed by machines, by artificial intelligence capable of maintaining the equipment and forwarding the data. But the readers, the civilizations that consulted this vast and silent library, would never meet each other, would never exchange a thought in real time, would never know whether the minds whose words they were reading still existed, or had long since fallen silent. This is the limit that emerges from every serious attempt to imagine interstellar communication. The constraint is not technology. The constraint is not power or precision or the difficulty of encoding meaning across cultures. The constraint is geometry, the shape of space-time itself, the inviolable law that says nothing carrying information can travel faster than light. The best imaginable network, the most advanced relay system, the most patient and capable array of Bracewell probes. All of these can preserve knowledge and forward it across the centuries, but none of them can make neighbours of civilizations separated by light years. None of them can transform the sending of messages into the holding of conversations. None of them can bridge the fundamental isolation that the universe imposes on every mind within it. There is a moment encountered by anyone who thinks carefully about these matters, when the sheer loneliness of the situation becomes vivid, when the abstract constraint reveals itself as something felt rather than merely calculated. The galaxy might be full of life, full of intelligence, full of civilizations that have built great works and asked great questions and developed answers that would transform our understanding of everything. And all of that richness, all of that accumulated wisdom might be separated from us by walls of time so thick that we could spend the entire future history of our species trying to reach it and never succeed, never manage more than the exchange of a few slow letters, never achieve anything that could be called a meeting of minds. And yet there is something in that loneliness that is not entirely dark. The same geometry that isolates us also connects us in its way. A message sent across the light years is still a message. A library staffed by machines is still a library. The knowledge that other minds exist, even if we can never meet them, even if we can never share a moment with them, is still knowledge, still a transformation of the human condition, still an answer to the ancient question that has haunted us since we first looked up at the stars and wondered whether we were alone. The confirmation that we are not alone, that other minds have asked questions and found answers, that intelligence is not a local accident but a feature of the universe itself, would be a gift beyond measure, even if it came wrapped in the recognition that the givers were forever beyond our reach. But there is a darker possibility, a shape that the isolation might take that would be harder to bear. What if the evidence comes and it cannot be followed? What if the signal arrives and it is singular, unrepeatable, a voice that speaks once and then falls silent forever? On the 15th of August 1977, a telescope in Ohio recorded something that has never been explained. The telescope was called Big Ear, a flat reflector the size of several football fields, operated by Ohio State University and dedicated, among other things, to the search for signals from other worlds. It was not a pointing telescope. It could not be aimed at a particular star and held there. Instead, it relied on the rotation of the Earth to sweep its beam across the sky. A slow scan that covered the heavens once each day, recording whatever signals fell within its narrow window of sensitivity. The astronomer who found the anomaly was not present when it happened. Jerry Eman was a volunteer, a scientist who gave his time to the project because he believed in its importance, and he discovered the signal several days after the fact, while reviewing the computer printouts that recorded everything the telescope had heard. The printout was a grid of numbers and letters, each character representing the intensity of the signal at a particular moment, a kind of chart of the radio sky as it drifted past the telescope's beam. Most of the characters were low, ones and twos, the quiet hum of the cosmos. But at one point in a single column, the characters climbed suddenly, rising through the numbers and into the letters, reaching a peak so far above the background that Eamon circled it in red ink and wrote a single word in the margin. The word was wow, and the signal has carried that name ever since. What Big Ear recorded that night was a burst of radio energy at a frequency of 1420 megahertz, very close to the emission line of hydrogen. The frequency that physicists had long suggested would be a natural choice for interstellar communication, a kind of universal channel where any technological civilization might think to listen. The signal was strong, more than 30 times the intensity of the surrounding noise. It was narrowband, confined to a sliver of the spectrum so thin that it seemed almost designed, almost artificial, nothing like the broad spectrum emissions of natural sources, and it lasted exactly as long as it should have lasted if it came from a fixed point in the sky, exactly 72 seconds, the time it took for the Earth's rotation to carry the telescope's beam across a single spot in space. Everything about the signal suggested artificiality. Everything about it was consistent with what searchers had hoped to find. And yet, in the decades since the August night, no one has ever found it again. Big Ear itself continued to scan the sky for years, sweeping back across the same region, listening for a repeat, and heard nothing. Other telescopes, more sensitive, more powerful, have pointed at the same patch of sky, at the stars that lie in the direction from which the signal seemed to come, and they too have heard nothing. The Breakthrough Listen project, the most comprehensive search for extraterrestrial intelligence ever undertaken, has trained its instruments on the region, using the great dishes at Green Bank and Parkes, listening with a sensitivity that dwarfs anything available in 1977, and it has found no trace of the signal, no whisper, no echo, nothing at all. There are natural explanations. There are always natural explanations. The region of sky where the signal appeared contains clouds of interstellar hydrogen, and recent research has proposed that under certain rare conditions, a burst of radiation from a transient source, perhaps a magnetar flaring in the distance, might trigger a sudden brightening of that hydrogen, a kind of cosmic maser that could mimic for a few seconds the signature of an artificial signal. It is possible that what Big Ear heard was not a message at all, just a coincidence, a fluke of physics that happened to look like the very thing the searchers were looking for. But the explanation remains uncertain. The signal has never been seen again, and without a second detection, without a chance to study it further, to measure its properties, to confirm or deny its artificial origin, the question cannot be resolved. The WOW signal exists in a kind of permanent ambiguity, neither confirmed nor refuted, neither explained nor mysterious, a single data point that might be the most important observation in human history, or might be nothing at all. And this ambiguity points to something deeper, something that the geometry of isolation makes almost inevitable. In a universe where signals take decades or centuries or millennia to arrive, where the sources of those signals are changing and moving and perhaps falling silent while the light is still travelling, the evidence of other minds might come in forms that can never be verified, that can never become the foundation of contact or conversation. A signal that appears once and never repeats is a voice without a dialogue, a message without a return address, a hint that something might be out there but no way to find out what, no way to follow up, no way to turn the tantalizing possibility into confirmed knowledge. The WOW signal was heard almost 50 years ago, and we are no closer to understanding it today than we were then. If it was a message that came once and never came again. A greeting from a civilization that either moved on or fell silent or simply chose not to repeat itself. If it was natural, it was a natural phenomenon so rare and so specific that it has not recurred in half a century of watching. Either way, it stands as a reminder of what the universe might offer and what it might withhold, of the possibility that evidence of intelligence might arrive in forms that enforce rather than relieve our isolation. But there is a still darker possibility, a shape that the future might take that is harder to imagine and harder to bear. What if the evidence were unmistakable? What if the signal were not a single burst but a sustained transmission, not ambiguous but clear, not a hint but a declaration? What if, tomorrow or next year or a century from now, a telescope on Earth detected something that could not be explained by any natural process, something that carried the unmistakable signature of intelligence, something that included perhaps mathematics or images, or a reply to something we ourselves had sent? Imagine for a moment that the signal came from a star 1,000 light-years away. That is not an unreasonable distance. The Milky Way is 100,000 light-years across, and 1,000 light-years would place the source within our own modest corner of the galaxy, within the population of stars that our signals have not yet reached, but that older civilizations, if they exist, might have been watching for far longer than we have been broadcasting. Imagine that the signal contained mathematics, the universal language, patterns that could not arise by chance, sequences that demonstrated intelligence on the far end. Imagine that it contained images, representations of the world that sent it, its landscapes and inhabitants, its machines and its arts. Imagine that it contained, most hauntingly of all, a reply to something that human beings had sent centuries ago, a response to a message launched in antiquity, to a radio broadcast from the early days of our technological civilization, to something that left Earth long before anyone now alive was born. The world would change. The confirmation that we are not alone, that intelligence exists elsewhere in the universe, that another mind has looked out at the stars and wondered about us, just as we have wondered about them, would be the most significant discovery in human history. The questions that have haunted philosophers and scientists and children staring at the night sky would finally have an answer, or at least the beginning of an answer, a data point where before there was only speculation. And yet, even in that moment of triumph, the geometry would assert itself. The signal came from 1,000 light-years away. The light that carried it left its source 1,000 years ago. The civilization that sent it, the minds that composed the message and aimed it at Earth, existed a millennium before the message arrived. By the time human scientists decoded the transmission, the senders might have changed beyond recognition, might have evolved or transformed or fallen, might have become something that would not recognize itself in the message it had sent. The portrait of themselves that they included in the transmission would be a portrait of ancestors, of a version of their civilization that had passed into history while the light was still travelling. And if Earth wished to reply, if the scientists who received the message composed an answer and aimed it back at the source, the answer would take another 1,000 years to arrive. By the time the senders received it, if they still existed, if anyone was still listening, 2,000 years would have passed since the original message was sent. 2,000 years of change, of growth, of transformation, of the countless alterations that time works on any living thing. The conversation, if it could be called a conversation, would not be an exchange between contemporaries but a correspondence across millennia, a dialogue between ghosts and inheritors, between civilizations that would never know each other as they truly were, only as they had been long ago, when the light first left its source. This is the climax that the geometry of the universe imposes on every dream of contact. The confirmation that we are not alone would also be the confirmation that we are alone in time, that the minds we might reach are separated from us by gulfs so vast that meeting them is impossible, that sharing a moment with them is impossible, that anything resembling friendship or collaboration, or the exchange of ideas in real time is forever beyond our grasp. We would know that they existed, or had existed. We would know that they had asked questions and found answers. We would know that intelligence was not unique to Earth, that the universe had produced minds elsewhere, that we were part of something larger than ourselves, and we would know at the same time that we could never touch them, never speak to them, never share with them the experience of being alive at the same moment in the history of the cosmos. The silence that fills the space between the stars is not merely the absence of signals, it is the presence of a constraint, a law written into the fabric of space-time itself, a geometry that permits existence but forbids communion. The civilizations that might be out there, scattered across the galaxy, each one wondering about the others, each one listening for signals and sending messages and hoping for some sign that they are not alone. Are all of them trapped within their own bubbles of causality, all of them isolated by the same inviolable speed limit that governs every photon and every thought? They might know of each other, they might send each other greetings and archives and portraits and legacies, but they cannot be neighbours, they cannot be contemporaries, they cannot meet. There is a question that has been asked, in different forms, for as long as humans have considered the possibility of sending messages beyond Earth, and it is a question that grows more uncomfortable the longer you think about it. If we are sending messages that will be received not by us but by our descendants, if we are composing transmissions that will arrive at their destinations centuries or millennia after we are gone, if we are addressing civilizations that exist in our past and will only learn of us in their far future, then who has the right to speak on behalf of humanity? Who decides what we say and what we include and what portrait of ourselves we send outward into the silence? The question is not abstract. It has been asked out loud in conferences and academic papers and public debates, and it has never been satisfactorily answered. In the autumn of 2010, the physicist Stephen Hawking, a man who had spent much of his life thinking about the universe and our place in it, made a public statement that surprised many of his colleagues. He said that humanity should be cautious about sending signals into space. He said that contact with an advanced extraterrestrial civilization could be dangerous, that we had no way of knowing the intentions of beings who might receive our messages, and that history had shown what happens when a technologically advanced culture encounters a less advanced one. He used the word risky. He suggested that it might be wiser to listen than to broadcast, to remain quiet and observe rather than announce our presence to whatever might be out there. The statement was controversial. It was discussed widely, debated in scientific journals and in the popular press, and it highlighted a tension that had been simmering for decades within the community of astronomers and scientists who thought about these questions. There were those who believed that humanity had an obligation to reach out, to send messages, to attempt contact even if the reply would take generations to arrive. and there were those who believed that we should be careful, that we should think about the consequences, that we should not assume the universe was a friendly place. The debate was not new. It had been going on in various forms since the early days of radio astronomy. But Hawking's statement brought it into the public eye, and it forced people to think about the stakes. The question was no longer just whether we could make contact or whether we should listen for signals. The question was whether we should transmit deliberately, whether we should send powerful, focused messages toward nearby stars, whether we should do more than simply leak radio noise into the cosmos. The term for this practice was MITI, Messaging Extraterrestrial Intelligence, and it was distinct from SETI, which was passive, which listened but did not speak. MITI was active, it was intentional. It was a decision to say something, to address someone, to reach across the silence and announce that we were here, and that decision, once made, could not be unmade. A message sent could not be called back. A transmission, once it left the antenna, was beyond human control, racing outward at the speed of light, carrying whatever information it contained, representing whoever had sent it, for as long as the signal remained detectable. There were people who devoted their careers to this question. One of them was a man named Douglas Verkoch, a psychologist and astronomer who had spent years thinking about how to compose messages for extraterrestrial audiences, how to encode meaning in a form that beings with no shared language or culture might be able to decode. He became an advocate for MITI, for deliberate transmission, for the idea that humanity should not simply wait in silence, but should actively attempt to initiate contact. He argued that the risks were overstated, that the galaxy was already filled with evidence of our existence, that any civilization capable of receiving our signals and travelling to Earth would already have the technology to detect us, and that remaining silent would not make us any safer. He argued too that there was something profoundly human about the act of reaching out, about the attempt to communicate, about the hope that someone somewhere might hear us and understand. In 2017, an organisation he led sent a message toward a star called GJ273, a red dwarf 19 light-years away, orbited by a planet that might be capable of supporting life. The message was designed carefully, encoded with mathematical and scientific information, and transmitted at high power. It would take 12 years to arrive, if anyone was listening, if anyone received it, if anyone composed a reply. That reply would take another 12 years to return, 24-year round trip at minimum. The people who sent the message knew that they might not live to see a response. They sent it anyway, but there were others who were not convinced. They asked who had given Verkoch, or anyone else, the authority to speak for Earth. They pointed out that no government had authorized the transmission, that no international body had debated it, that no democratic process had approved it. The message had been sent by a small group of scientists and private donors, acting on their own initiative, deciding for themselves what to say and where to send it. And the consequences of that decision, if there were consequences, would be borne not by the senders but by everyone on Earth, by future generations who had no voice in the matter, who could not vote or object or revise the message, who would inherit whatever response arrived, decades or centuries later, without having had any say in whether the message was sent at all. The problem was acute. The people most likely to receive any reply were children who had not yet been born, or their children, or their children's children. The senders were addressing the future on behalf of the present, and they were doing so without the consent of the people who would actually have to live in that future. This was the ethical weight of MITI. It was not simply a question of risk, though risk was part of it. It was a question of representation, of who has the right to speak, of what obligations we owe to people who do not yet exist. The question had been asked before, in different contexts. It had been asked about environmental policy, about nuclear waste storage, about any decision whose consequences extend beyond the lifetime of the decision makers. But in the context of interstellar messaging, the question took on a particularly stark form because the timescales were so long, because the messages were so irrevocable. because the act of transmission was simultaneously an act of legacy building and an act of speaking for people who could not speak for themselves. Every civilization that chose to send a message into space faced this problem. They had to decide what to include, what to omit, what portrait of themselves to present to unknown recipients in an unknown future. They had to decide whether to tell the truth or to idealize, or to simplify. They had to decide what values to emphasize, what knowledge to share, what impression to leave. And they had to do all of this knowing that the people who would receive the message would judge them by it, would form their understanding of humanity or of whatever species had sent the message based on the contents of that transmission, and that there would be no opportunity to explain, no chance to clarify, no follow-up message to correct misunderstandings. The problem was not just political, it was intimate, it was personal. Because if messages were for descendants rather than contemporaries, if transmissions were acts of witness rather than conversation, then what we chose to send became a question of what we thought was worth preserving. What we believed was essential about ourselves, what we hoped would endure. It became a question of legacy, of how we wanted to be remembered, of what we thought future minds should know about us. And that question, when you asked it seriously, was almost unbearably difficult. Should we send our achievements, our science, our art, our music? Should we send our languages, our histories, our stories? Should we send our failures, our conflicts, our mistakes? Should we present ourselves as we wish to be, or as we were? Should we be honest or aspirational? Should we assume that the recipients would be sympathetic, or should we assume that they would be indifferent or even hostile? Should we send a message at all, or should we simply remain silent, letting our electromagnetic noise speak for us, letting the universe decide whether we were worth noticing? There were no clear answers. There was only the recognition that the decision mattered, that it carried weight, that it was not something to be done casually or thoughtlessly. And yet, despite the difficulties, despite the ethical complexities, despite the absence of consensus, messages had been sent. The Arecibo transmission in 1974, the Voyager Golden Records in 1977, the message to GJ273 in 2017. Each of them was an attempt to say something, to leave a trace, to address someone beyond the horizon. Each of them was an act of faith, a gesture made in the absence of certainty, a choice to reach out even when there was no guarantee that anyone would ever reach back. And each of them, in its own way, was an answer to the question of who speaks for humanity. The answer, in each case, was a small group of people acting on their own initiative, choosing for themselves what to say and where to send it, and trusting that the message would be received in the spirit in which it was intended. It was not a perfect answer. It was not a democratic answer, but it was the answer that had been given again and again, because the alternative was silence. And silence felt like surrender, felt like giving up on the possibility of contact, felt like accepting the isolation that the geometry of the universe imposed without even trying to resist it. Consider for a moment the Arecibo message. It was transmitted on a late autumn afternoon in 1974, beamed toward a globular cluster called Messier 13, a dense sphere of hundreds of thousands of stars located 25,000 light-years away. The message itself was brief, lasting less than 3 minutes, consisting of a little over 1,600 bits of binary data arranged in a grid that, if decoded correctly, would reveal a series of images. There were numbers, the counting numbers from 1 to 10, represented in binary. There were atoms, the chemical elements that make up DNA: hydrogen, carbon, nitrogen, oxygen, phosphorus. There was a diagram of the DNA molecule itself, a double helix, the shape that carries genetic information in every living thing on Earth. There was a human figure, stick-like and simplified, with an indication of height, roughly 14 radio wavelengths, which translated to about 1.7 meters. There was a diagram of the solar system, with the third planet offset slightly to indicate that it was the origin of the message. And there was a representation of the Arecibo telescope itself, the instrument that had sent the message, with a note of its diameter. The whole message was a portrait, a snapshot, a way of saying we are here, this is what we're made of, this is what we know, this is how we know it. The message was designed by Frank Drake, the astronomer who had conducted the first modern search for extraterrestrial signals, and by Carl Sagan, the astronomer who had spent much of his career thinking about life beyond Earth and how we might communicate with it. They knew, when they sent it, that it would take 25,000 years to arrive, and that any reply would take another 25,000 years to return. They knew that the message was not a realistic attempt at conversation. They said so, explicitly in interviews and in papers. They described it as a demonstration, a symbolic act, a way of showing what was possible, a way of marking the occasion of the telescope's upgrade, a way of saying that humanity was capable of this kind of communication, even if the communication itself would never be completed. It was theatre, in a sense, but it was also more than theatre. It was an act of witness. It was a way of saying that we had been here, that we had looked outward, that we had tried to reach beyond ourselves. It was a message not just for the recipients, whoever they might be, but for the senders, for the people on Earth who wanted to believe that contact was possible, that the universe was not empty, that somewhere, among the uncountable stars, there might be other minds looking back. The Voyager Golden Records were similar in spirit but different in execution. They were designed not for transmission but for physical carriage, bolted to the sides of two spacecraft that were leaving the solar system and would never return. Each record was a phonograph disc 12 inches in diameter, made of copper and plated in gold to protect it from the erosion of space, from radiation and dust and the long passage of time. The records were encoded with sounds and images, more than 100 photographs, natural sounds from Earth, thunder and wind and waves and the calls of animals, musical selections from cultures around the world and across centuries, and spoken greetings in 55 languages. There were written messages too, one from the President of the United States, one from the Secretary General of the United Nations, each of them addressing unknown recipients in an unknown future, each of them trying to convey something essential about humanity, about what we valued, about what we hoped for. The records were the work of a small committee, led by Carl Sagan and including Frank Drake, who handled the technical aspects, and Ann Druyan, who curated much of the music and wrote some of the text, and Timothy Ferris, who produced the audio, and John Lomberg, who designed the visual elements, and Linda Salzman-Sargon, who organised the greetings. They worked quickly, under pressure, with limited resources, and they made choices, hundreds of choices, about what to include and what to leave out, about which photographs to send and which sounds to record and which pieces of music to select. They knew that the choices mattered, that they were composing a portrait that would represent humanity for as long as the spacecraft endured, which might be billions of years. They knew that they were speaking not just for themselves but for everyone on Earth, and they knew that there was no way to get it right, no way to include everything, no way to satisfy everyone. They did it anyway. There was a phrase inscribed on the records, etched by hand into the metal, small letters running around the edge of the disc. It said, "To the makers of music, all worlds, all times." It was a greeting, a dedication, a way of acknowledging that whoever found the record, if anyone ever did, would be someone who understood beauty, who valued art, who knew what it meant to create something for its own sake, for the sake of the thing itself rather than for any practical purpose. It was a way of saying that we hoped the universe was full of such beings, and that we wanted to reach them, and that we believed that music, that art, that the things we made when we were at our best were worth preserving, were worth sending across the void, were worth offering to minds we would never meet. And it was also an admission of a kind, because the phrase did not say to the makers of music now. It said all times. It acknowledged that the record was not for contemporaries but for successors, for civilisations that would exist long after the senders were gone, for a future that the senders could not see or predict or control. It was a message across the generations, a gesture of hope and humility, a way of saying that we had existed, that we had learned something, that we had made something, and that we wanted someone, somewhere, someday to know. Carl Sagan spoke about this often. He said that the spacecraft would be encountered and the record played only if there were advanced civilizations in interstellar space, but that the launching of this bottle into the cosmic ocean said something hopeful about life on this planet. He said it knowing that the hope was fragile, that the chances of the record ever being found were vanishingly small, that the spacecraft was so tiny and space was so vast that the odds of an encounter were almost zero. He said it anyway, because the act of sending the record, the act of trying to communicate, was itself meaningful, was itself a statement about who we were and what we valued, regardless of whether anyone ever received it. The record was not a conversation, it was a testament. It was a way of saying that we had been here, that we had looked up at the stars and wondered, that we had tried to answer the questions that the night sky posed, and that we wanted to share what we had learned, however incomplete, however imperfect, with anyone who might come after us. This is what interstellar communication becomes when you remove the possibility of conversation. It becomes an archive, a legacy, a portrait sent forward in time, a message for descendants and inheritors and strangers who will live in a future we cannot imagine. It becomes an act of witness, of saying that a particular species existed, that it learned the cosmos, that it achieved a certain level of understanding, that it valued certain things and hoped for certain outcomes, and that it chose to address someone beyond its horizon, not because it expected a reply, but because the act of reaching out mattered, because the attempt to communicate was itself an answer to the silence. The messages we send, whether they are radio transmissions or physical artifacts, are not tools for making contact. They are monuments, they are markers, they are ways of saying that we were here, that we did this, that we tried. And perhaps in the end, that is enough. Perhaps the act of sending a message, of choosing what to say and how to say it, of deciding to reach across the gulf of space and time and speak to someone we will never meet, is itself a kind of communion, a way of participating in something larger than ourselves, a way of joining a chorus that spans the galaxy and the ages, a chorus in which each civilization sings alone but sings nonetheless, hoping that someone somewhere might hear, might understand, might remember. The universe does not permit conversations among civilizations. The geometry is too harsh, the distance is too great, the speed of light too slow, but the universe does permit something else. It permits listening, it permits witness. It permits the slow accumulation of messages and artifacts and signals, each one a voice from a particular time and place, each one a fragment of a larger story, each one a piece of evidence that minds had existed, that questions had been asked, that the work of understanding had been attempted. The civilizations scattered across the galaxy, if they exist, might never meet. But they might hear each other. They might send each other greetings and portraits and legacies. They might listen for signals and decode transmissions and learn, across the centuries, that they were not alone. The knowledge would arrive late, always late, separated by gulfs of time that make any shared experience possible, but the knowledge would arrive nonetheless, and perhaps, in the quiet that stretches between the stars, that knowledge is what matters. Not the conversation, but the confirmation. Not the meeting, but the memory. Not the companionship, but the recognition that other minds had looked up at the same sky, had asked the same questions, had sent their answers outward into the silence, and had hoped, as we hope, that someone, somewhere, would hear. The silence may not be absence, it may be patience, it may be the sound of a chorus so vast and so slow that no single voice can hear the whole of it. A chorus in which each civilization sings its part and then falls quiet, and the song continues, carried forward by others, by civilizations that rise and fall and rise again, each of them adding their voice to the long accumulating record, each of them listening for the voices that came before, each of them hoping that their own voice will be heard by those who come after. We are part of that chorus now, whether we intended to be or not. We have sent our signals, our plaques, our records. We have announced ourselves to the universe, and we have done so knowing that we will not hear the reply, that the conversation we hoped for is forbidden by the laws of physics, that the most we can hope for is that someone in some far future might find what we left behind and might understand, or might at least remember, that we were here. The spacecraft are still out there, coasting through the dark, growing more distant with every passing year, carrying their small golden discs into the space between the stars. They will continue for thousands of years, for tens of thousands, for as long as nothing disturbs them. They will pass through clouds of dust and gas. They will drift past stars that are still forming, stars that have not yet ignited, stars that have already died. They will travel distances so great that the sun, the bright familiar star that gave them birth, will fade until it is indistinguishable from all the other faint points of light that fill the sky. And through all of that, the records will remain, bolted to the spacecraft, gold and silent, waiting. They are messages for a future that might never arrive, for minds that might never exist, for a contact that the universe may not permit. But they are also something else. They are a record of us, of what we were, of what we cared about, of what we hoped for. They are a way of saying that we looked outward, that we tried to understand, that we chose to reach beyond ourselves, and that we believed, despite the silence, despite the vast indifferent distances, that the attempt was worth making. We have spoken. The universe is listening, or it is not. But we have spoken, and that is the only answer we can give to the silence that fills the space between the stars.